Welcome. So we're going to talk about distributed learning paradigms. So far we discussed training tasks that were like minimizing, let's say, some average loss, okay? Or more abstractly, we can talk about in terms of this expectation. Again, we can think of it as minimizing the average loss, okay? And when we discuss this, as well as the techniques when it comes to train deep learning models, so such as, again, learning rate tuning, normalization methods, regularization methods, advanced training algorithms such as momentum, variance reduction, and adaptivity. But our underlying assumption was that the data is all in one place, okay? So everything is in one place. But in many settings, the data is actually generated and is held locally by many devices or agents, okay? So for instance, each of us is using our phones to take pictures, to text, right? So therefore I have data in the form of images, videos on my cell phone. You have data in the form of images, videos on your cell phone, okay? And this is not necessarily something that we want to share with a different entity, okay? So due to privacy reasons, we may want to make sure that our data is held locally, okay? But maybe, like the phone manufacturer or the operating system manufacturer wants to leverage our data in a private way to develop other tools that are useful for us. For instance, maybe to develop AI algorithms that improve our image qualities, or maybe develop next word prediction AI models that help us text faster, okay, or write faster and better, okay? So we're going to talk about these scenarios where the data is generated and held locally by different agents or different clients, and we want to see what are some principles when it comes to training deep learning models in this setting, okay? And this setting, basically, we refer to it as learning from distributed data or distributed deep learning, okay? So this is basically a more mathematical way of talking about exactly what I talk about. So we still want to minimize the average loss, okay? But by average here, we mean the average over the entire agents, okay? Such that the local loss that each agent holds can be thought of as this average loss. So I have an average loss over my training data, you have an average loss over your training data, okay? And then the global loss is defined, let's say, as the average of my loss as well as your loss, okay? So again, the terminology therefore is that we call F in the context of distributed learning the global loss, while we call Fj's the local loss, okay? All right, so we're going to talk about three different paradigms that help us to leverage this distributed data, and we talk about their advantages and disadvantages. The first paradigm we want to talk about is what I call centralized learning, okay? So as the name suggests, what we're going to do, we're going to ask all agents to send their data as is, without any modification or anything, to a central entity, which we call a server, okay? Let me here state these two remarks. We're going to use server, aggregator, or fusion center to mean this central entity. Also, we may use agent, client, worker, participant, device, or node interchangeably, okay, to refer to as local data holders. All right. So therefore, centralized learning says that all agents send their data as is, without any modification to the server, as we are demonstrating here. So I have owner A, owner B, owner C. They send their data to the server, and the server does basically model training. So it takes care of the model training procedure. Okay. Okay. So what are the features of this paradigm? So obviously there is no data integrity. Okay. If you are sending the data without any modification, so the server gets to see exactly what kind of data we have. So it is therefore something to be careful about. This is a paradigm that may work in some scenarios and may not work in other scenarios. Okay, due to the again the loss in data integrity. We may suffer from communication issues if the data size is larger than the agent's capability. If I have like for instance, hundreds of images, but I don't have access to 5G, so I may not be able to, or I don't have access to Wi-Fi, I may not be able to send all of my images, right? So I cannot send them as is with high precision, high quality. There's also the issue of potential bottleneck at the server if there are many agents, okay? So if billions of agents, billions of nodes, billions of cell phone holders all send their data at the same time to the server, server may not be able to handle it. Okay. So on the plus side, however, typically, if we assume the server has access to very highly capable computational resources, the training procedure will be very fast and very accurate, right? Because we have access to lots of data, all at the same place, all, let's say, high quality. So we can do the training using the techniques we talked about very efficiently and accurately. All right. So the next paradigm is what I refer to as parallel learning, okay, which tries to sort of preserve some data integrity, okay. In particular, instead of sharing the raw data, agents share some model-based representation of their local data. So it's not raw data, it's processed data, basically, okay. And they're going to do this repeatedly by communicating something like gradient or similar quantities with the server. Okay? So it's a repeated process then. And the idea is that now the agents also participate in training. The training is not happening only at the server. Everyone, including the server, participates. And the idea is that we are basically utilizing the computational resources of agents to gain some again data integrity. Okay. So here is the one way to demonstrate this. Then, so we have different clients. Okay. Then let's say each one is participating in the training. They send some information using uplink to the uplink communication to the server. Server does some aggregation and then sends a message to the clients or agents using downlink communication, and then we repeat this process until we find a good model and our training process converges. Okay. A little bit more mathematically, this is basically what we want to do. Let's say we have capital T numbers of communication or training rounds. In each round, server sends, let's say, the current model, let's call it the current global model, W bar T, to agents. Each agent then is going to compute and send the gradient of this W bar, with respect to its local data to the server, or it's going to do a model update, let's say by using something like SGD or gradient descent. So it's going to update the global model WT bar according to its local data by running something like SGD or gradient descent, and it's going to send this updated vector, which now depends on the data that was that agent J in this case holds. Okay. Nonetheless, after agents perform some local computation and send those messages using uplink communication to the server is going to aggregate the received messages and update the global model. Okay. A simple aggregation mechanism is just average. So that I'm writing here. So it means that this is how the server is going to update the global model. If the clients were sending the gradient, the server would take the average of these local gradients and then use it in something like gradient descent or SGD to update the global model. On the other hand, if the clients were sending their updated model, the server could aggregate those updated model by just simply taking the average of them. All right. So let's talk about some features of this parallel learning paradigm. So as we mentioned, we have some improved level of preserving the integrity of the data because we are not communicating raw data points anymore. We are sharing some representation of the data through gradient or model updates. We are taking the advantage of local computations, right? So these days we are holding edge devices, IoT devices that have GPUs and CPUs. So they could actually participate in training for the sake of preserving data integrity. On the other hand, we may have some communication issues, especially if the model sizes are larger than the agent's capability. So the agents are repeatedly communicating with the server and they are sending gradient or model. Gradient has the same size as the model, basically, right? So if I have a billion parameter model, this is not something I can do, okay? So it's going to be very, very costly for my agents. So this gives rise to this whole field of model pruning, okay? So how can we develop AI models and use them in edge devices, okay? So with limited power, limited communication, and limited computation capabilities. Okay. Another potential issue is the issue with the bottleneck at the server. Again, if there are many clients, many agents, all communicating with the server at the same time, server may not be able to handle it. Okay. And there is also a delay issue, potential delay issue due to stragglers if we have a synchronous system. Synchronous system means that the server is going to wait for everyone to send their messages and then, let's say, perform aggregation. So maybe I have one client that is more capable than the other client. So it's going to have to send a message, wait for the server to aggregate the messages received by everyone, and then send a message back to me. And this naturally will cause some delay in training. Okay. So therefore, this is again an issue that gives rise to this problem of designing asynchronous parallel learning methods. Okay. All right. So we talk about this aggregation mechanism, right? So in the simple case, I'm just talking about the average. Okay. So server is basically applying the averaging operator to aggregate the messages received by received from the client. Okay. So we call this basically an aggregation mechanism, and this is something that we can generalize. So the averaging operator is basically maximizing the utilitarian welfare, but you can define other mechanisms based on other notions. For instance, you can basically maximize the egalitarian welfare, which basically means minimizing the worst case loss. So therefore, it is not surprising to note that there is an active area of research in terms of designing different activation mechanisms with different goals in mind. Okay, so if you want to be fair, for instance, first of all, what's the notion of fairness, and what's the best activation aggregation mechanism according to that specified notions of fairness. Okay, or if you want to be robust, let's say with respect to the drop in communication noise, maybe malicious activities, what's the most robust aggregation mechanism? So these are all areas where there's been active research happening in the past few years. All right. Now let's talk about the next paradigm, federated learning. So this is basically can be thought of as the approximating parallel learning to reduce communication and computation requirements by trading off some accuracy and precision. Okay. So there are two distinguishing features here. The first feature is periodic communication. In particular, instead of communicating local gradients or local model updates, as we talked about before, after one local step, we're going to do it after, let's say, capital E number of steps, where E is larger than 1. Okay. So for instance, this is what we'll do. Let's say that the global model WT bar is sent to the clients. The clients take this as their initialization and then run, let's say, something like SGD or stochastic gradients for capital E number of iterations, as opposed to just one iteration in the case of parallel learning. And then afterwards, they're going to basically call the resulting model their local model, and they're going to communicate that to the server. Okay. So this is basically this can be thought of as approximately solving the task of minimizing the local loss. Okay. So in particular, basically, what we would send to the server after capital E number of local updates is an approximation of the solution to the local loss. Okay, so that's the first feature. And the reason I'm talking about approximately solving the local loss is that, for instance, instead of using SGD or gradient descent, you could use different algorithms, right? So all is required here is to send an approximate solution of the local loss to the server. All right, so that's periodic communication. So as the name suggests, we have periodic communication. The other distinguishing feature is that we have partial participation. Compared to parallel learning, where we required everyone to participate in each communication round, here we have partial participation, meaning that every round we only ask a subset of clients of size R, where R is significantly less than N, to participate. And then that means that the aggregation only happens over the messages sent by the participating client at that specific communication round. Okay, so I'm taking the average over basically subset S as opposed to the entire pool of clients. All right, so that's also that's another paradigm. Federated learning resembles some similarity with parallel learning, but it basically leverages two approximation methods to improve communication efficiency as well as computation efficiency. Okay. Now, in distributed learning, there are some issues related to heterogeneity. Okay, so, and in particular, we have two issues or two kinds of heterogeneity: hardware heterogeneity and statistical heterogeneity. So, hardware heterogeneity means that agents may have different communication and computation capabilities. Okay, so in terms of computation, for instance, that could mean that one agent will be able to do more local steps than another agent. In particular, let's say E sub I is strictly larger than E sub j. Okay. In terms of difference in communication capabilities, so this could mean that, for instance, agent I could be able to participate more frequently than agent J, or it could mean that agent I can send higher precision messages, meaning it can send more bits compared to agent J. Okay. So this leads to some fairness issues, right? Because the current solution we talked about is going to favor more capable clients. Therefore, an active area of research is to basically develop fair distributed learning paradigms for instance, fair federated learning algorithms, fair parallel learning algorithms, etc. Okay. So the other issue is what we refer to as a statistical heterogeneity. So the idea is that each agent holds different loss functions because they have different data points, different data, which means that the I is not necessarily dj. Okay? And as a result of this, as well as the fact that in federated learning we are using partial participation and periodic communication, we may suffer from convergence issues. Okay. Now, this is actually something that we can handle using some of the techniques we've talked about in the class before. Okay. So to do that, basically, let's start by revisiting our simple aggregation mechanism, which was basically taking the average of the messages sent by the client. So this is the aggregation happening at the server. Okay. Now, here I am assuming that each agent is running locally, let's say gradient descent with capital E number of iterations. Okay. Now I'm gonna basically write this in this form by factoring out the common terms. Okay. So I have basically the following that says that the next global model is the current one minus some step size times another quantity, which I'm calling basically the average of some GIs. Okay. The point is that this basically resembles SGD's update. So this is very similar to SGD. Okay. So SGD suffered from high variance, okay, due to the variance of the stochastic gradient. Here it turns out that simple averaging is actually suffering from variance arising from statistical heterogeneity, as well as the fact that we are using partial participation and periodic communication. So because we were able to deal with the variance of SGD using the momentum procedure and variance reduction, it turns out that we can actually extend those techniques to the setting of federated learning to tame the detrimental impact of statistical heterogeneity, as well as partial participation and periodic communication. So therefore, we can, for instance, mimic momentum, as I mentioned, to design more effective aggregation mechanisms. All right. So now let's talk about the final paradigm, and that's called decentralized learning. So the idea is that here there is no server, there is only peer-to-peer or P2P communication, okay, from between the agents. So effectively, each agent is serving as its own local aggregator, okay. Now, more mathematically, when we say peer-to-peer communication, we are saying that the communication among the agent is governed by a graph. So the graph means that, or determines how the agents are connected, or which agents can communicate with each other. Okay, so here is some examples of the communication graph that I'm showing. For instance, it could be like a ring, it could be a grid, could be exponential, it could be fully connected, meaning that everyone is connected to each other. It could be directed, it could be undirected, etc. Okay, but the point is that, and it's also an intuitive point, I would argue, that if you have lower graph connectivity, then you have a slower propagation of information, and therefore a slower convergence. Okay. Because if I have a message and I want that message to be sent to this guy, it's going to take longer to get here. Whereas in a fully connected graph, there is a direct line between these two. So the agent can receive my message in one iteration or in one shot. Okay. Furthermore, if the graph has lower degree, then there is a lower communication bottleneck and a lower delay. Okay, and finally, in the case of decentralized learning, we can again talk about the issue of synchronicity and also asynchronicity. Okay, so synchronicity still could be an issue leading to some to some delay issues, as we talked about before in the context of parallel learning as well as federated learning. All right, so let's see, for instance, a simple example of this decentralized learning procedure. Okay, so let's say n sub j is the set of neighbors of agent I, and neighbors are basically agents that can that have a direct communication with agent I, and know that I is also a neighbor to itself. Okay, so a simple algorithm that we can run to train the deep learning model in a decentralized learning paradigm is as follows: that each agent computes and sends the aggregation of the messages that is receiving from its neighbors. Okay, so in particular, I'm mentioning two choices here. So first choice is that to find the next update, you aggregate whatever message you're receiving from your neighbors, and then let's say run a local gradient descent kind of an update. Or let's say that everyone first updates their parameter locally using something like gradient descent, and then they share the messages with each other. So therefore, you are aggregating the model updates, okay, as opposed to the previous models. Okay. So, and this is basically a paradigm we're going to talk about a little bit more in the next lecture in terms of the convergence analysis and also basically the role of the communication graph. But before that, I want to make basically a couple of remarks. The first remark is that and these two remarks are basically they aim to imply that decentralized learning is a more general framework than federated learning and parallel learning. Okay, so if I have a fully connected graph with no server node, this is essentially equivalent to having a star graph with a server. Okay, so this is a star graph, let's say with a server with 3 agents. So this is in some sense equivalent to basically having a fully connected graph, right? Because server ensures that the messages are aggregated, or message of agent 1 is accessible to message of agent 2 after one shot. And this is exactly like having a fully connected graph. Therefore, we can think of parallel learning as an example of decentralized learning. It turns out that federated learning is also an example of decentralized learning, where instead of having a fixed communication graph, we have a sequence of potentially disconnected time-varying graphs. Okay, so again, in federated learning, we have sort of a star graph where not all, but a subset of the clients participate in each iteration. So this is again something that's similar to having, let's say, a sequence of time-varying graphs. So let's say this is at time 1, this is at time 2, this is at time 3, etc. Okay, so this graph is basically indicating that at time 1, only 2 of the agents are participating, let's say agent 1 and 2. This graph, on the other hand, says that at this communication round, agent 2 and 3 are participating. And finally, in this example, at time 3, all agents are participating, etc. So therefore, federated learning can also be thought of as an example of decentralized learning. For this reason, we want to spend a little bit more time to understand decentralized learning when it comes to its convergence guarantees. So we're going to have discussion in the next lecture. I'll see you there.